So transformations of quadratics. This is one of my favorite parts about quadratics, is the getting to see the different things that happen. Before you start, there's a copy of these notes on Edline if you want to go get them, if you're one of those people who likes to have the graph so that everything can be neatly placed on a graph and not just sketched. If not, you can just sketch it. It'll be just fine. It will also help if you have different colors so that you can draw, because we're going to be drawing several things on a graph at a time, and if you have different colors, it'll help you distinguish. You don't have to use different colors, just a suggestion. Transformations, if you will remember from 7th pre-AP or before that, there are three types of transformations we talk about in junior high. There are translations, which slides the image up, down, right, or left. It doesn't change the size or the shape or anything. And then there are reflections, which flip it over. And then there are dilations. The only two we're going to deal with today are translations and reflections. We will not dilate our parabolas, but we are going to translate them and we are going to reflect them. So let's talk about the parent function really quick. I know that we have already, but it's just a good reminder so that you don't forget, because everything is going to be based on the parent function today. Everything we do will go back to the parent function to answer the question. So the equation, if you remember, is y equals x squared. And if I fill in a table based on that function, negative 2 squared is 4, negative 1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. And that makes it so that I can plot these points on a graph. And so I have negative 2, 4. I have negative 1, 1, 0, 0, positive 1, 1, and positive 2, 4. So this is what my parent function looks like. It is a parabola, of course, because they are all parabolas at this point, whose vertex is at the origin, right there at 0, 0, and the axis of symmetry, or the line of symmetry, is the y-axis. So that's what makes it the parent function. It's got to have a vertex at the origin, and the y-axis is your axis of symmetry. Domain and range, really quick. The domain, since I got the arrows on either end, is going to be the negative infinity to positive infinity. And you can still write it that way, but I'm going to start writing it like this because that means all real numbers. It's the same thing, but that is a shorter trip. But if you still want to do the negative infinity to positive infinity, they mean the same thing, but just so you know, those are the same thing. My range starts down here at the bottom at 0 and goes all the way to infinity. So basically it is all numbers 0 and up. So my range is y is greater than or equal to 0. If you want to write it as 0 to positive infinity, that works too, but this is how I'm going to start writing domain and range. It's shorter, it's easier, it encompasses everything. That way you're used to it. But this is what the quadratic parent function looks like. Okay? Everything we do today is based on that. So let's do a few transformations. This is the parent function. You should notice it has the vertex at the origin. The y-axis is the line of symmetry. We're going to take and we're going to graph 4 separate equations on this same graph so that you can see what's going on. I will do my best to use colors that show up. We will see. It would help too if you had your calculator out, just because doing the calculations might help. You do not have to, but it would help if you had it out. So we're going to graph x squared plus 3. I'm going to make a little table here. And I'm just going to use this table over and over and over. I'm going to make a bigger table because I don't think that one's going to do what I want. But I'm going to make a table here. And I'm just going to use this table over and over for each of the 4 equations that I have here. That way I can see what's happening. And every time I am going to plot the points negative 1, 0, and 1. I think that those 3 points will be enough to do what I need. If they are not, I'll add in negative 2 and positive 2. But for this first equation, x squared plus 3, if x is 1, negative 1, negative 1 squared is 1, and 1 plus 3 is 4. 0 squared is 0, plus 3 is 3. And then 1 squared is 1, plus 3 is 4. So I have these 3 points I'm going to plot. So I have negative 1, and 1, 2, 3, 4. I have 0 and 3. And I have 1 and 4. If I connect these points, you should see I have now made a parabola. And so if you compare this parabola to the parent function, the one that was already drawn, remember, I said we weren't doing any dilations at all, so the size of the parabola isn't going to change. Despite the fact that my drawing is really crappy and it's not a very good parabola, the size of the parabola doesn't change. The width of the parabola, the height of the parabola, none of that changes. The only thing that I am changing is its position on the graph. And if you will look, I went from the parent function right here with the vertex at 0 to my new function that has a vertex of 3. And so all I did was take this parabola and slide it up. So I slid it up, and I slid it up 1, 2, 3 places. So how did the graph change compared to the parent function? Here is how we are going to say that. It translated up 3 units, because that's what happened when I added 3. It took my parabola, scooted it up 3 units. So let's do the next one, the x squared minus 2. I'm going to pick a different color this time, so let's do the red. X squared minus 2. Now, if x squared is negative 1 squared is 1, and 1 minus 2 is negative 1. And then if it's 0, 0 squared is 0, minus 2 is negative 2. And if I plug in 1, I go back to negative 1, because these two will always be the same. The square of a negative is the same thing as the square of the positive, as long as you are squaring the actual negative. So I'm going to plot these points. So I have negative 1, 0, negative 2, and 1, negative 1. And if I connect these points, you should see I made another parabola. Again, this parabola, the width did not change. All that happened was it moved down. And if you will look, from comparing to the parent function to the new one, it scooted down 1, 2 units. And so I say that it translated down 2 units. So if you will look, when I add a number, when I went from x squared to x squared plus 3, because parent function is x squared. When I add a number to the parent function, it translates the function up that number of units. And when I subtract a number from the parent function x squared, it translates the parent function down that number of units. So if I want to summarize, I know there are 2 more functions here, and you can go graph them if you want, but if I want to do a summary, here's what my summary is going to say. Okay, if I add or subtract a number, it translates my function up or down that many units. So, adding or subtracting from x squared translates the function up if you're adding, or down if you are subtracting that number of units. And this is true for all functions. It doesn't necessarily have to be the parent function we're moving, but it's good to compare everything to the parent function, because that always stays the same and doesn't change. But adding or subtracting always moves the function. It just translates it. It doesn't change the size or anything like that. It just moves it up or down. Okay, next example. This is still the parent function. It just looks a little different because my graph, you don't see the whole graph. We just have the we mainly see this quadrants 1 and quadrants 2 because we don't need this bottom half. It's not going to affect anything. So now what we're going to do is we're going to, instead of adding or subtracting a number to x squared, we're going to multiply a number times x squared. So our first one, we're going to do the same thing we did a minute ago. We're going to make this pretty table, and we're going to plug in numbers. So now instead of x squared, I'm going to do 3x squared. So I'm going to multiply it by 3. So if I plug in negative 1 here, I end up with 3 times negative 1 squared. Order of operations says exponents first, so negative 1 squared is 1 times 3 is 3. 0 squared is 0 times 3 is 0. And then 1 squared is 1 times 3 is 3. Before I graph this, I am going to have to apologize because at the beginning I said we weren't going to do dilations, and I was wrong. We are going to dilate. So we have negative 1, 3. We have 0, 0. So the vertex is in the same place. And then we have 1, 3. So I have not changed the position of my parabola at all. What I have done is I have left it in the same place, so its vertex is still, that is such an ugly parabola. Its vertex is still at the origin, but what I have done is I have taken it by multiplying it by 3, I have squished it in, okay, and so I have made it skinnier. And so if I want to compare this graph to the parent function, what changed is the graph is narrower. So I made it more narrow. So by multiplying x squared times 3, I have taken the graph and I have made it narrow. So let's do another one. I'm going to skip down here to the third graph, the 1/2 x squared, and we're going to do the same thing with it. So negative 1 squared is 1 still, and 1 times 1/2 is 1/2. 0 squared is 0 times 1/2 is still 0. And then 1 squared is 1 times 1/2 is 1/2. So here's my new one. So I have negative 1 and 1/2, so it's here. The vertex is still at 0. And then I have 1 and 1/2, which is right here. And so if I connect these points, you can see, again, it didn't move up or down. It stayed in the same place. My vertex is still at the origin. The y-axis is still my axis of symmetry. But now instead of being my graph, the parent function, the same width, now it has gotten wider. So what happened when I multiplied by a fraction or a number less than 1 is the graph got narrower. I left a word out before. Didn't get narrower. This one got wider. So when I add a whole number or a number larger than 1, when I multiply the x squared by a number larger than 1, my graph narrows. If I multiply x squared by a number smaller than 1, the graph widens. So if I'm going to summarize, we're going to go up here and create a summary. Okay? So multiplying by a number larger than 1, the graph narrows. I think I write too fast and it doesn't have time to record. Then if I multiply by a number smaller than 1, the graph widens. And that's what you need to get from that. If you want to graph the other two and see, so that you can see that that's really what happens, go right ahead. So let's do one more set of examples and see what happens now when I put it all together. So again, with the pretty little table, I have x and y, I do negative 1, 0, and 1. So let's do this negative x squared again. This is my parent function graph for me already. This is going to be negative x squared. So when I plug this in, I'm going to write over here so that you can see I have negative 1 squared, because I'm squaring negative 1, but it also, they want me to do the opposite of x squared. So when I do negative 1 squared, it becomes 1, but if I'm going to take the opposite of that, the way the function is written, it's negative 1. If I do 0 squared, I have the opposite of 0 squared. Well, 0 squared is 0, and the opposite of 0 is still just 0. And then when I do positive 1 squared, I have the opposite of 1 squared. Well, 1 squared is 1, and the opposite of that is negative 1. So when I plot these points, I have negative 1, 0, 0, and 1, negative 1. And so when I graph this, hopefully you will see what happened. My vertex remained in the same spot. My vertex is still at the origin. Y-axis is still my axis of symmetry. So I have not, I didn't move it up or down. I also did not make it wider or narrower. Hopefully you drew your graph better than mine and you can see that this is the same width. The only thing that happened is my graph is now flipped over. And so what do we call it whenever we flip over the graph of something? What kind of transformation or transformation is it when I flip the thing over like I just did? It becomes a reflection. And so if I want to describe this transformation, this one is reflected. And if you want to get real specific, you can say it is reflected over the x-axis. We are not going to get that specific because it's not always that. It's very clear for this one it was reflected over the x-axis. It's not always.